Welcome to Manufacturing Processes, Machining and Machine Tools lectures by Professor Joyjeet Ghose. This is the third lecture of a series of lectures. This lecture will be on geometry of single-point cutting tool. He will be discussing the defining angles, nose radius and the significance of the angles of single-point cutting tool. Also American Standard Association system method of designating a single-point cutting tool. That is tool signature of a single point cutting tool. So, do not miss and watch the full video. For the next video in the lecture series, please click the suggested video link above. You may also click on the playlist at end of the video to access all the videos. Please subscribe this channel and yes, do not forget to like and share. Also click on the bell icon to receive instant information of new videos uploaded. Thank you.
Hello friends, welcome to lecture 3. In this lecture, we'll be discussing about single point cutting tool and specifically the geometry of a single point cutting tool. Now, in first two lectures, we have discussed about the introduction to metal cutting and we have discussed about the mechanics of orthogonal metal cutting. Now, one of the most principal tool that is used in metal cutting is a single point cutting tool. Single point cutting tool means there is only one cutting edges. And there's a particular geometry that allows it to cut smoothly on any machining operation, and that geometry we'll be discussing. And this is not a fixed geometry. The geometry can be altered according to your requirement. So we'll start with the lecture. So this is how a single point cutting tool looks. I'll go into more better diagram. So this is a figure of a single point cutting tool which I have taken from Kalpakjian book. So here, remember there are 6 angles which are important for us to know, and these 6 angles along with the radius of the nose that defines a single point cutting tool uniquely. So what are the 6 angles? See, this face is inclined backwards like this. So this is the back rake angle. Simultaneously it is inclined sidewise. It is the side rake angle. So this face, this is the side flank and this is the flank, and this is called the face. The face is inclined downwards, the back rake angle, plus it is inclined sidewise, it is side rake angle. So 2 angles on this face and 2 angles on this side flank and 2 angles on this side flank. So here the side flank is inclined downwards in this manner so that it does not touch the workpiece. That is the clearance angle we have discussed in the tool chip interference model. So it is that clearance angle. So it is inclined backwards. So that is the end cutting end relief angle. And also it is, as it is inclined in this direction, it is inclined in this direction also. So it is inclined in this manner. So you can see here. So it is in this direction. So that away inclination is called the end cutting edge angle. That away inclination is the end cutting edge angle. So what happens as the tool moves forward, it prevents this edge from rubbing against the machine surface. And this side is also inclined in this direction. So this side is also inclined in this direction. That is called the side relief angle. So it is inclined in this direction because as it is moving in this direction, so this will prevent, during longitudinal fit, it will prevent this side from rubbing against the workpiece. And simultaneously, it is inclined in this direction. It is inclined in this direction. It is not straight here. It is inclined in this direction. And that angle is called the side cutting edge angle. That angle is called the side cutting edge angle. You can see here, this face, this flank is inclined slightly here. It is not coming in this direction. So this angle is called side cutting edge angle. So this side cutting edge angle, this is the cutting edge basically. With this cutting edge we will be cutting. So as it is inclined, you can see the length of the cutting edge increases. So the life of the tool also increases. So we keep it up to certain point of certain angle. If you keep it beyond that certain angle, then it will chatter. So this is the side cutting edge angle. Influence of each of the angles we'll be discussing. And This is slightly rounded. See, if it is perfectly sub, obviously it will fracture, so you keep it slightly round. This round nature not only prevents the fracture or concentration of stress at the tip of the tool, but it also gives a white surface here. So this rubs or removes the feed marks of during the metal cutting. So same thing I have discussed in isometric view. This is the top view, front view, and the side view. If you look from the front side, so the angle that is visible to you is that the face of the tool is inclined backwards, and you measure it with plane parallel to the shank of the tool. So this angle is called the back rake angle, and the angle by which it is inclined sideways is called the side rake angle, visible from the side, visible from the side. So this is the side rake angle. So combination of this, or the resultant rake angle is of the resultant of the side rake angle and back rake angle is called the rake angle. So this is the side relief angle, angle by which the face, the side flank is relieved like this. This flank is relieved, the side relief angle, and this angle is called the end relief angle, and angle by which this face, the side face, is inclined away is called the end cutting edge angle. So this prevents, as this tool is moving in this direction for longitudinal feed, so this will prevent this side from rubbing against the finished machined surface. So this angle is also provided. So this increases the length of the cutting edge. This is the cutting edge. Now the load will be applied over a larger area, and therefore increasing the life of the tool. Therefore we include side cutting edge angle up to certain degree. Beyond it, it will cause chatter. Chatter is a vibration that occurs in the tool and the workpiece. Okay, this was a positive rake angle because the rake angle is in this direction and rake angle is in this direction. This is positive rake angle. So in this case, both are negative rake angle. So both are negative rake angle. Negative rake angles are also useful in certain cases. Okay. This is a model that I have prepared in Pro-E. Okay, so what is back rake angle and side rake angle? I have said that the resultant rake angle is derived from the back rake angle and side rake angle. So what is the importance of this rake angle? Now the rake angle allows a passage for the chip to flow conveniently. It determines how much power will be required in metal cutting. So if you increase the rake angle, the power required will be less. So rake angle allows chips to flow conveniently in convenient direction, reduces the cutting forces, and provide keenness to the cutting edge and improves the surface finish. Now there are certain advantages of having a positive rake angle. The positive rake angle reduces the compressive force, friction, yielding thinner and less deformed, and most importantly cooler chip. So this gives a better surface finish, but it reduces the strength of the tool. It reduces the strength of the tool. This is because, so here, if you keep on increasing the rake angle, so if you keep on increasing the rake angle, the leap angle will decrease. So if the leak angle decreases, the strength of the tool decreases. So that is a factor. Now, negative rake angle. So negative rake angle, the strength of the tool obviously is more. However, the problem with this is that it produces a highly compressed chip having high temperature, and the chip has a very rough surface. So now the question is, if this has so many problems associated with negative rake, why to take negative rake angles? Okay, the negative rake angles are essential when you are machining with brittle tool material. Brittle tool materials like ceramics and carbides. When ceramics and carbides are used as cutting tool, now these ceramics and carbides are highly brittle, and what happens if we give positive rake angle or higher rake angle, then these are likely to fracture. So in order to increase the life, we incorporate negative rake angle. Now obviously, as I have told, negative rake angle increases the cutting forces that is required, but these tool materials like ceramics and carbides can be used at a very high cutting speed. Now, since they are used at a very high cutting speed, it is seen that at a higher cutting speed, the cutting forces required decreases significantly. So, in a sense, it compensates in that manner. So, therefore, by using those type of materials, we use negative rake angle or less rake angle. Now, obvious question comes: what are the factors on which we will be selecting a rake angle? This question will come in the minds of the students. That okay, fine. Then how will select the rake angle? So, several factors are associated in selection of rake angle. These are type of material being cut. The harder the material, like cast iron, may be machined by a smaller rake angle than required by soft material like mild steel or aluminum, where you can go for higher rake angle. Type of tool material, as I have said, some brittle material requires negative rake angle or less rake angle. So that is another factor. The depth of cut, how much depth you are applying. Say if the depth of cut is more, obviously you should select. That means the load that will be applied by the workpiece on the tool will be high, so it requires lesser rake angle or negative rake angle. And the condition of the machine and rigidity of the tool holder. If the condition of the machine is very old, then in likely chance it will vibrate. So once the tool and the workpiece vibrate, so large amount of load is acting on the tool, and tool is likely to fail by fracture. So in such cases, it is better to use negative rake angle or lesser rake angle. So there are several factors based on which we select the rake angle, but you don't have to worry. As a machinist, there is often handbooks that are available for particular combination of tool and the workpiece material and the cutting speed that you are selecting. There is a recommendation of rake angle, and you can select a rake angle. And one more thing, as I have said, if you keep on increasing the rake angle, there is a video on it. You can go through the video. If you keep on increasing the rake angle, the cutting power that is required will decrease. Now then, at what point should you stop? The thing is that there is experimentation has been done, and it has been seen that if you keep on increasing, the cutting force required decreases. But after a certain angle, the cutting force does not decrease much, but whereas the strength of the tool reduces significantly. Therefore, normally we keep it around 10 degree to 25 degree max, the rake angle. The relief angles, as I have said, relief angles already I have discussed, basically to provide relief to reduce the interference between the tool and the workpiece. These are the side cutting edge angle and end cutting edge angle. Also, end cutting edge angle also basically a relief angle. Nose radius also I have discussed, slightly rounded to avoid the concentration of the stress and fracture of the tip of the tool, and to remove the feed marks, increases the strength of the cutting edge. Okay, the tool nomenclature that we have discussed till now is American Standard Association tool nomenclature. There are different standards of designating tools. The nomenclature that we have discussed and the way angles are represented is given in American Standard Association, and that is what I am discussing here. There are several other methods which I have not discussed here. You can refer to any good books on metal cutting, and you will find out how tool angles are represented in different standard systems. So tool signature in American Standard Association system is a sequence of numbers listing the various angles and the degrees and the sizes of the node radius. So how do you designate a tool? I designate a tool by American Standard System, orthogonal rake system. There are various available systems are American Standard System, orthogonal rake system, normal rake system, and maximum rake system. So the American Association system represents tool signature like this: back rake angle, side rake angle, end relief angle, side relief angle, end cutting edge angle, side cutting edge angle, and nose radius in this particular sequence. I repeat: back rake, side rake, end relief, end cutting edge angle, and side cutting edge angle, followed by the nose radius in mm. So if this is the tool is designated by this sequence of numbers, then I can say the nose radius is 1 mm, back rake angle is 8 degree, and side rake angle is 14 degree. Likewise, the other angles. So this is how we designate tools, single point cutting tools, particularly in ASS system. So with this, we come to the conclusion of this lecture. I hope the geometry of single point cutting tool, which is a very complex geometry, And I would recommend, if you are good in CAD modeling, 3D modeling, try to model a single point cutting tool. You will find it extremely difficult because each plane is inclined at 2 angles. So it is very, very difficult. So try to do it. So this will clear your concept also. And I hope you understand how to designate a single point cutting tool in American Standard Association system. So thank you for watching this video. I hope you have liked it.